So in contrast to methods that are actually constraining the policy improvement step or actually constraining the policy in learning, there is another idea. And the other idea is actually to estimate the value function more conservatively in order to be lower bounded or upper bounded in the error when you estimate the Q function. Okay, so the basic idea or the basic assumption is that different areas of the Q functions are associated with different degrees of uncertainty. And in Baire and BCQ, you address this uncertainty by restricting the policy to the areas, to certain areas, or at least to areas where you're thinking that you're certain with respect to your value function. And the question is, how else could we actually address the problem of uncertainty? And the idea of CQL, so conservative Q learning, is posed like this. So instead of constraining the action set, which is basically what we did with BCQ and Baire, is to constrain or is actually to be conservative in the estimation of state action values that are not part of a data set. So imagine that. So this was actually also from the Baire blog in here, and this is actually showing you two Q functions. So the orange dashed line is the 2Q function, and you see that in a certain area in here you have a support in your data set because you have the actions are part of the data set, okay? And this means that in this area you have a very decent or very certain estimate that the estimated Q function is approximately correct. And you have like areas aside your action support where the bets are just off. So you have a model and the model approximates the Q function, but the values that you approximate in here are not grounded with ground truth values from your data set. And this means that we actually in Baire and BCQ restricted the policy improvement step to actions that lie within the support. The idea of CQL is actually to not restrict the action set to the set, but to be conservative in the estimation of the Q function in areas that are not within the support of the actions in the data set. In other sense that what we did in the beginning, what we did in the previous lecture, so we have the policy constraint where we actually constrained the methods in the policy improvement step. We now tackle the problem in the policy evaluation step. In the policy evaluation step, we actually estimate the value function, and what we actually want to do in here, we want to be conservative in the areas of uncertainty. And if we are conservative enough, this implicitly keeps the policy away from these out of distribution actions. Because if we are conservative, these areas in here will not actually bootstrap positive errors into the Q function and not pollute our state space. So the idea is basically to learn a value function such that the estimated performance of the policy under this learned value function lower bounds its true value. Okay, how is CQL actually achieving that? So the goal is actually to find the lower bound of Q pi using data D collected from our behavior policy. So this is what we have seen also before. Let t hat pi be the empirical Bellman operator for the policy pi estimated from the dataset. And what CQL in principle introduces is a so-called CQL regularization. And what we actually want to do is we want to minimize QSA on states that are from D and actions that are sampled from the policy, not the behavior policy, okay? So we want to have a minimization of the Q function if the states are within the data set and the actions are sampled from the policy that we are training. However, if the actions are sampled from the behavior policy, so if we have support through our action set in the data set, there is no need to be conservative. If this is the case, we additionally maximize, okay? So let's just combine these two steps. So the CQL optimization problem for policy evaluation just looks like this. So we want to minimize Q. There's alpha is a trade-off parameter to trade-off conservativeness. So we want to minimize the expectation of these formula, and this is the standard Q learning update. So we want to minimize Q if the states are sampled from the data set and the actions are sampled from the policy. So we want to minimize this one. Minus, meaning in this sense maximizing, for all the actions that are actually part of the data set. Okay? So if they are part of the data set, we want to maximize, and in principle we want to minimize them. And we want to actually reweight also with the standard mean-squared-Bellman error that we use in Q-learning. So take a look at this, maybe pause the video at this point and look at the formula, but if you like, read it over and over again, it really starts making sense at some point. So the basic idea is that we generally want to minimize the actions that are sampled from our policy in bootstrapping. However, we want to maximize them much more if we consider actions that are also part of the data set. Okay, so we want to make things, we want to correct minimization. We want to correct minimizations by maximizing them if they are part of the data set. Okay, so that's maybe the best way to actually describe it. Okay, so this is the CQL optimization problem for policy evaluation, and but in the end, we want to actually find a good policy pi from the offline data. So that's the actual goal. So we want to do conservative control. And what we actually always do is we iterate between policy improvement and policy evaluation. And we can actually do that jointly. So, so this inner target is still the minimization goal here. And what we actually want to do is here, we actually sampled the action from our policy pi. And we want to actually define our policy pi using, we described it by mu, and we want to maximize we want to maximize the actions that are actually optimizing our targets. So we want to maximize the actions that we select in our policy, but we want to minimize the Q function. So it's just an outer loop in the optimization target, but we can actually describe it like this to make it end-to-end differentiable. And then we can actually do the policy improvement by using an actor in standard Q-learning, so just like we did it in something like DDPG. Okay, so if you do something like this, looks much more conveniently in practice. You can also see that using such methods, you're still able to outperform methods such as Baire and BCQ on well-known data sets. So this is AntMaze. So AntMaze was the problem we also had in the beginning. We have a small ant that is tasked to go through this 3D environment. And to order in the data set, we usually see settings that are where you only have subtrajectories and you get data from those subtrajectories, and you need to stitch them cleverly together to actually come up and actually solve the problem properly. And you see that using conservative offline RL, you're able to solve much more environments that policy constraint methods are not solving. And you actually get a decent result if you apply methods such as conservative Q-learning instead of policy constraint methods such as BCQ or Baire. Okay, so this is just for reference, giving you a little bit of an insight how standard actor critic and CQL relate to each other. But important is that you understand in CQL you're trying to get a lower bound of this of the Q function by minimizing all the Qs that are not part or minimizing all the Qs and maximizing all the Qs much more if the actions that you bootstrap are part of your data set. Okay, and it's of course only a regularization term because you still have because you still have in here the standard Q-learning mean-squared-Bellman error in here. Okay, another conservative method is to use something like model-based offline RL. And the basic idea of model-based offline RL is actually to estimate a reward function and a transition model from the data that you have in your data set. And then if you have that, you can apply active reinforcement learning to the model. From the perspective of the agent in training, the transitions that you actually obtain from your model can now collectively be online. So you just query your dynamics model so you don't have a distribution shift. The problem is that pi might become very different from pi prime. and you will query your model in unknown areas. And you have seen that if you do that, you need to account for that somehow, because in that areas your model will give you wrong returns and wrong probabilities. And the basic idea is actually that you actually come up with a way to measure the uncertainty of your model. We have seen that in model-based RL. Uncertainty quantification is a well-known problem that you can really do. And what you actually do is you learn the uncertainty quantification on your data set, and you apply the active learning RL agent, and depending on the uncertainty of your model, you actually discount or punish the reward that your model actually gives. So you just formulate an active RL setting, and you provide a reward to the agent, and if you have a high uncertainty on your reward model, then you actually subtract a little bit of that reward depending on how uncertain you are. And if you do that, you also implicitly keep the agent away from areas where you're uncertain about the reward structure of your environment. So this is also a very nice idea to somehow view the offline RL problem more like a black box thing. So you just try to learn a model that represents the data from your data set. And if you're uncertain with the areas that your agent is currently exploring, you actually drive down the reward to keep the agent away from these areas. There is also a little bit of work coming on top of that. There's a nice idea of combo. It's also not part of the exam because we don't have much time to talk about that. But the idea is actually similar to what we have also seen in model-based RL. So all of these concepts are, of course, captured in here because it's model-based policy optimization. And the idea is also to do something like an MBPO, where you just augment the data that you have using rollouts from your model. So in this case, you combine CQL using the dataset and rollouts from your model to actually weigh this minimization, maximization a little bit, and you can actually augment the data that you use using your CQL objective. If you are interested, dig through it. However, we will not go much into detail when we talk about combo and offline RL. However, you also see in here that using things like MOPO or combo actually lets you outperform on a well-known environments even more than CQL outperforms BCQ and Bear. Okay, maybe come to a conclusion at this point. So we have seen that offline RL is a very nice idea because we need to do offline RL to actually use RL in much more applications where we currently or where we are not allowed to do a trial and error paradigm because there is human involved and danger, and we cannot really risk so much to do an active learning strategy. So we want to actually apply offline RL to get agents by resorting to a lot of offline data that has been captured by expert policies, expert humans, random policies, or things like that. And we want to actually, and the idea is actually that we do not want to copy what's in the data, so we want to actually find good behavior in a data set that might contain good behavior, but that also might be completely containing bad behavior. And this means that we want to generalize to similar states and actions that are not really part of the data set, but that are close to the data set, and we want to actually improve by making these small differences to the data set. And another concept is also that this also relates to is that we want to stitch together good and bad behavior to come up with solutions that are, as it is, not part of the data set. And this is the simple A, B, C, or 1, 2, 3 environment in here, where you see that you want to be able to stitch two behaviors that are both not optimal together in order to reach the goal starting from 1 and going to here. Okay. So this is it for offline RL. There's also a lot of references and reading material to it. So if you are really interested, I recommend you using the Berkeley blogs on offline RL. So the Berkeley group is very active in offline RL. I have them referenced in Bear and BCQ. So they make really nice introductions on their blogs. There is also a nice Medium blog posts in here that you might look into. And there's also a nice tutorial on offline reinforcement learning from Sergey Levin. This is this one in here. So Levin and Kumar and Tucker and Fu, offline reinforcement learning tutorial review and perspectives and open problems. This is a very nice introduction, has around 50 pages, and it reviews also the problems and the policy gradient side and the value-based side. And this really gives you a great overview of the problems and perspectives of offline RL.